whether we can find de Sitter solutions of string theory, and also to ask whether those solutions could possibly be so numerous that they could account for the smallness of the vacuum energy. And as we've heard, and as you know well, constructing a controllable de Sitter solution in string theory is difficult, it's subtle, and there's some contested progress in models with few parameters, small numbers of instabilities, but small numbers of dynamical fields, where the risk of an instability is more easily addressed. But generally speaking, instabilities are extremely common. And the goal of this work is to try and get a broader picture of the landscape of possible de Sitter vacua by using random matrix theory to understand statistical properties of de Sitter critical points. So we'll start with critical points rather than assuming that we're dealing with vacua. Let me stress particularly, we're going to be using the structure of supergravity and ultimately through supergravity, the structure of the effective theories derived from string theory in looking at the form of these critical points. So one thing we can ask with a statistical perspective on de Sitter critical points is what fraction of critical points are vacua? And where in the landscape should we look if we want to be successful? What are some sorts of characteristics of regions of parameter space where a search for de Sitter vacua is more likely to succeed? So I'll first say a few things about critical points in supergravity. I'll then give you a brief summary of the key concepts from random matrix theory. And then I'll come to the main results, which are split into two parts. I'll talk first about generic critical points, by which I mean critical points at which the supersymmetric masses are not parametrically large. And then I'll talk about the qualitatively different critical points where the supersymmetric masses are very large and there's a better shot at stability. And then if there's time, I'll give a discussion of a couple of applications. So first, critical points. I'll be talking about an n equals 1, d equals 4 supergravity theory with n here, chiral superfields, so n complex scalars. And for the purpose of this talk, I will only talk about f-term supersymmetry breaking, so I'll leave out the d terms. And all the critical points that we'll be considering will be critical points at which supersymmetry is spontaneously broken by an f-term. So perhaps at the end in the applications, I'll talk about scenarios with uplifting by explicit breaking effects, but for essentially all of the talk, the breaking is going to be spontaneous breaking by f-terms of the moduli themselves. So if we want to study the stability of de Sitter critical points, we just have to study the Hessian matrix. So we just have to start differentiating this familiar object and defining useful notation as we go so that we can see some matrix structure. So first step is that at a critical point, of course, the first derivative vanishes. I'll define this notation. Curly d is the Kähler plus geometrically covariant derivative. And if we now define the following objects, z, so the notations that I'll ask you to remember through the talk are these, z and u. Z is the double derivative of the superpotential, and u is the triple covariant derivative of the superpotential. And they'll be appearing all over the place, so it's better to have simple expressions for them. So if I introduce these, and I also, working at one particular critical point, use Kähler and coordinate transformations to set the metric to be the identity and the Kähler potential to be 0, then I can start to simplify the form of the Hessian matrix. So the Hessian takes the following form. It has some pure blocks, i.e. with only holomorphic or only anti-holomorphic indices, and some Hermitian blocks. And the pure blocks involve this object u, the triple derivative of w, and also f. And in the Hermitian blocks, we also get contributions from the Riemann curvature on the field space. Okay, so this is just a simple consequence of differentiating vf. And what we're going to do is we're going to try and express the Hessian matrix as a sum of simple matrices. We're going to pick out some structure hiding there. So you can decompose the Hessian matrix that I just showed you as a sum of 4 terms. First term is the supersymmetric term. Supersymmetric term involves the Hermitian square of this matrix Z, which is the double derivatives of W. And so this matrix in particular is positive definite. So that plays a distinguished role. Next piece is a pure piece involving some more derivatives. There's a piece involving the Riemann curvature. And then there's a piece that I'll ignore in the rest, which is just a shift of the overall spectrum. So since we're trying to find the shape of the eigenvalue spectrum, this is easy enough to account for, and I'll suppress it. Although, of course, we incorporate it in the calculation. Okay, so since we've broken H into these blocks, we now have to ask, well, what are the constituents of the individual blocks? So the statistical approach that I'm going to pursue is the following. We're going to treat the superpotential and the Kähler potential as random functions. By random function, I mean specifically that the Taylor coefficients at the critical point are independent, identically distributed random numbers. So independent is clear. Identically distributed means that each of the Taylor coefficients of W and K is drawn from some statistical distribution, but it's the same distribution for all of the coefficients. So if I pick a convenient basis in which the F that is picked out by the F term, so Fa is delta A1 F times a phase, and again I use coordinates in which the metric is the identity, then the expression for the random supergravity picture we have here is the following. Z is given by any of the entries of the Z matrix is given by the supersymmetric mass scale times a random draw from some distribution omega that has mean 0 and standard deviation 1 over square root n. Now, it will certainly be an issue. One should think, does it matter which distribution do I take? And once I tell you a little bit more about random matrix theory, it'll be clear it's not going to matter what the distribution is. I'll keep it general for now, but if you like for definiteness, you can imagine that this is a normal distribution with mean 0 and standard deviation 1 over square root n. So for the second and third derivatives of W, I take this distribution, and similarly for the third and fourth derivatives of the Kähler potential. And this is enough to specify the Hessian matrix. So we're now in a position to study the distribution of critical points statistically using random matrix theory. And let me tell you just a few of the key facts about random matrix theory, although Gary has already given a number of the insights that are relevant for this analysis. So the essential idea of random matrix theory is that if you have very limited statistical information about the entries of an n by n matrix, you can still make incisive statements about the eigenvalue spectrum of the matrix, as long as n is large. In particular, the statements about the eigenvalues include the form of the eigenvalue spectrum for a typical matrix in the ensemble, but also, more relevant for us, the probability of a fluctuation to an atypical configuration. In other words, you can ask how atypical exactly is a particular kind of eigenvalue spectrum in the ensemble. The important phenomenon of universality is the matrix analog of central limit behavior. And what universality does is it ensures that the outputs, these computable quantities, the eigenvalue spectrum and the fluctuation probabilities, are independent of the inputs, namely the unknown statistical distribution of the matrix entries. So this is a very well-attested property, and it's something that we'll be able to confirm precisely and explicitly is relevant in our system. Now, when I say that the outputs are independent of the inputs, well, what do they depend on? They depend on just the symmetries of the matrix. So they don't depend on the statistical properties of the inputs, but at least they depend on the gross symmetries of the matrix. And matrices with simple symmetry properties fall into well-known and much-studied classical ensembles. So I'll review for you the two classical ensembles we need for this work, and then I'm going to build the Hessian matrix as a collection of matrices from known classical ensembles. So the first one is the one that Gary's already told you about, the Wigner ensemble, or the Gaussian unitary ensemble. This is the ensemble of Hermitian matrices, M equals A plus A dagger, where the entries of the matrix A are independent and identically distributed and drawn from some distribution. So I'd like to tell you a little bit about the eigenvalue repulsion effect that Gary mentioned, and that plays a critical role in the phenomena I'm going to be describing. So let's consider the probability of observing a given matrix M. So the probability of some M is given by, well, the product of the probabilities F of Mij of each of the matrix entries Mij. And so if these are drawn from some normal distribution, then you can easily compute what this probability is. But representation in terms of the matrix entries is not the convenient way to do things. The efficient thing to do is to convert to a basis in which you can just look at the eigenvalues. And when you do that, you get a Jacobian. And after keeping track of the Jacobian, you get a joint probability density, which is the probability for the eigenvalues lambda 1 through lambda n. And it takes the following form. There's an exponential of minus lambda squared plus this all-important log repulsion term. What this term is telling you is that configurations in which the eigenvalues are very close to each other, in which any pair come and nearly coincide, are disfavored statistically. So this is how we can be quantitative about how eigenvalue repulsion works. So if you take matrices of this form and determine the eigenvalue distribution at large n, you obtain the famous Wigner's semicircle law, depicted here. So throughout the talk, I'll be using red curves to give analytic results, and the colored stuff underneath is a histogram from simulations of the matrices in question. Okay, one more classical ensemble. The other one that we need is the Wishart ensemble. This consists of Hermitian matrices of the form A dagger, where A's entries are independent and identically distributed. Since it's the Hermitian square of some matrix A, M is non-negative. And at large n, the eigenvalue distribution takes a known form, which is called the Marchenko-Pasteur law. And here's some expression. You don't need to pay much attention to the actual expression. What's relevant is that it's positive definite and sharply peaked at 0. So now that I've reviewed these matrix ensembles, I'm going to build the Hessian matrix out of classical matrix ensembles. First, we're going to talk about generic critical points. What I mean by a generic critical point is one at which the various derivatives of the superpotential are not hierarchically separated. Okay. What I'll talk about later is a case where the supersymmetric masses, Z, are very large compared to F. This is a case with very much enhanced stability properties because unbroken supersymmetry gives complete stability. This is the generic case. Now, I hope it's plausible that this configuration, where these various derivatives of W are of the same order, is generic, but we prove in our paper that this is in fact the case, that these are generic. If you now use just this one identity about the Riemann tensor, a contribution that I previously called H curvature, which involved the curvature tensor, splits into two pieces, and now we can see 5 different contributions to the Hessian matrix. First one is the supersymmetric mass matrix, which I showed you before, and you now recognize it as a Wishart matrix because it's of the form Z dagger, where Z was the double derivative of W. The pure and K4 pieces, K4 is just diagonal fourth derivatives of the Keller potential, are Wigner matrices. The contribution from the square of the third derivative of the Keller potential is another Wishart matrix, and then there's this unimportant shift. So what we see is that the Hessian matrix can be approximated as the sum of 2 Wishart matrices and a Wigner matrix. The sims here are a little bit important. I'll be working with a model in which I equate the Hessian matrix to the sum of a Wishart matrix, and a Wigner matrix. I say sim here because, for example, you note that this matrix Z is symmetric, and the matrix A that I invoked in introducing the Wishart ensemble was not necessarily symmetric. So it's close, but there are a couple of very fine differences, and I'll show you how much difference those make. Okay, so we have a picture of what the Hessian matrix is, and our model is this. How can we get any mileage out of this? Well, the spectrum of a sum of matrices can be obtained from the spectra of the constituents of the sum. So let me explain that. Suppose you have some matrix A and some matrix B, and you know the spectrum of A and the spectrum of B, and you'd like the spectrum of A plus B. Well, since they don't commute, you can't just add the two spectra, but you can perform what's called a free convolution, which is the analog for matrices of an ordinary convolution for standard single variables. So the model then is that the eigenvalue spectrum of the Hessian matrix will come from the free convolution of the semicircle law spectrum and 2 copies of the Wishart spectrum. Again, I stress, of course, it's not just the sum of these spectra, which would be trivial to obtain and quite inapplicable. Okay, so sparing you all the details, we obtain an expression. Here it is. First, this is the eigenvalue density, rho of lambda. So this is the curve that overlays any of the histograms of eigenvalues. That's what the eigenvalue density means. First, omega is a parameter that measures the scale of the amount of SUSY breaking. It's just relating W to F. So it's telling you what the vacuum energy is. And the psi that appears here is some function. And in turn, the tau that appears in psi is some function. And you put it all together and you get some complicated expression. And now you can take that expression and you can compare it to simulations, and the match is essentially perfect. So it perfectly overlays simulations. Here, this is for 200 by 200 matrices. So I'm considering a model with 200 complex scalar fields. This stuff underneath is from simulations of the full Hessian matrix. not making any simplifications, not, when I said that these various constituents, I said sim here, these are approximate relations. I'm simulating the full structure to get the result here, whereas the analytic curve comes from making those approximations. And you can see the approximations are very good. So in sum, we have a strong support for an analytic model of what the Hessian matrix is and what its eigenvalue spectrum is. So now can we learn something from that? Well, the first thing is you see that 0 is here, so there are tachyons. But remember, this thing describes a typical configuration, and we'd like to know how atypical is a configuration in which there aren't any tachyons. And that's not found by just looking at this and finding the area under the curve from here to 0 and comparing to the area there, right? Because the eigenvalues are correlated. You have to ask a much harder question about fluctuations of the whole configuration. So as Gary nicely reviewed, there's this general fact in random matrix theory that eigenvalue repulsion strongly correlates the eigenvalues, and it makes fluctuations unlikely. There's a rich, well-developed theory of small fluctuations, the Tracy-Whittam theory, but a fluctuation to positivity in our ensemble, a fluctuation all the way from this edge to 0, something that makes the whole spectrum positive definite, is not a small fluctuation. So we can't use the Tracy-Whittam theory, we have to use the more recent theory of Dean and of Majumdar and collaborators, initiated in Dean and Majumdar. So for the analytic model, the Wigner plus Wishart model, we can actually show analytically that the probability of positivity is proportional to a constant times n squared. So the immediate conclusion is that an overwhelming fraction of critical points are saddles rather than local metastable minima. Recall that n is the number of moduli here, so it doesn't matter quite what c is. The c's that we find depend on this scale omega, so that's why I haven't put a number there, but they range from 10 to the minus 1 to 10 to the minus 2. Whereas n could be, for example, 100, and then you clearly have a stupendous suppression. Now, this is consistent with, but it's not trivially implied by, the same result for the fluctuation probabilities of the Wigner matrix and the Wishart matrix separately. So those are well-known results. And now we can put them together and we can say that even for the full structure of supergravity, which involves this, the free convolution of the Wigner and Wishart spectra, the fluctuation probability is indeed suppressed as a Gaussian. As I said, our model makes some simplifications, but we do have simulations of the full Hessian matrix making no approximation. And for those simulations, we also have strong numerical evidence. So inspired by the fact that the result is literally Cn squared for the model, we'll use the parameterization Cn to the p for simulations of the full mass matrix. And we find, so here's the log scale, up to n of 1,000, we find the result is very strongly consistent with p equals 2. Okay. So as Gary pointed out, a simpler model that really shows you a lot of the physics of these fluctuations involves a positive diagonal matrix plus a Wigner matrix. And for that case, Azami and Easter argued that P is approximately 2, and Gary and company confirmed that and discussed the role of this sort of structure in uplifting of type 2A vacuum. Okay, so that's the discussion of generic critical points at which the derivatives of the superpotential are of the same order. Let's move to approximately supersymmetric critical points. In approximately supersymmetric critical points, by this I mean that the supersymmetric masses are large, so the barriers that you expect, the instabilities are expected to be tamed by large supersymmetric masses. Denif and Douglas pointed out in 2004 that this is a particularly fruitful corner of the landscape for looking for de Sitter vacua, for precisely the reason that I said, the thought of stability. But as we heard in the talks by Bobby and Gordy, there is always a lighter field in theories of spontaneously broken supersymmetry, the superpartner of the Goldstino. So that's one scalar field, or two real potential instabilities. The critical point equation forces the Goldstino directions to have their supersymmetric mass contributions linked to the Gravitino mass. So they can't be parametrically heavy. And so even in this supersymmetric corner of the landscape, we don't have to worry about n possible instabilities, but we at least have to worry about one complex instability. Well, since it's just one complex instability, you can just try and write down the mass as a function of these various derivatives of the Keller potential and superpotential that I've defined. And Denif and Douglas did this. And in terms of that, they estimated the probability of stability, and then the estimate is that probability is proportional to 1 over n. So this should be contrasted to the Gaussian suppression that one finds in random matrix theory. But it's not unbelievable that the result could be like this, because after all, this is a very nearly supersymmetric case, and there is only one potential instability. But what was not entirely included in that result was repulsion, eigenvalue repulsion, of all of the heavy eigenvalues, the heavy n-1 eigenvalues, on the superpartner of the Goldstino. They push it down. When you incorporate that, you find that there's a negative definite contribution to the masses squared, which is parametrically dominant at large n. So the exact form is not that important, but what you can see here is this looks like perturbation theory, right? These lambda, what are the lambdas? The lambda b primes are the second through nth eigenvalues of the supersymmetric mass matrix. These are positive quantities, and they act to push down the smallest eigenvalue through the repulsion phenomenon. In pictures, how this looks is this. This is the statistical distribution of the smallest mass squared, the most unstable direction. Here's 0, if you omit the eigenvalue repulsion effect. And if you incorporate it, you get instead this blue curve. Here, the purple thing is the eigenvalue repulsion term itself. So you see that it's a vast change from a distribution that only has a very slight tail toward negative values to a distribution that is essentially fully supported at negative values. Okay, so what does this mean for the probability of positivity in this approximately supersymmetric corner? Well, instead of 1 over n, one finds, this is work by my student Johannes Bausch, one finds the probability is proportional to e to the minus constant n log n. Not e to the minus n squared, but still a pretty substantial suppression. Note that this is not so far off from the estimate Gary gave of decoupled fields, which was 1/2 to the n, or e to the minus n log 2. So there's still a landscape. Let's talk about the extent to which you can get around our assumptions. You know, to what extent have our conclusions said something about the full string landscape, or even just the string landscape at all? Well, first of all, we took w and k to be random functions of all their arguments with independent, identically distributed derivatives. And universality is a very strong guide here. It strongly suggests that if you make small changes to these assumptions, our results will survive. There are analytic results in this direction. We can also test it directly. We've explicitly verified that our results do survive if we change the input distribution. We don't take it to be a normal distribution, but we take something to be non-Gaussian. We take it to be a wide range of appropriately bounded distributions. You get the same result. Another thing you could try and do is you could introduce correlations in the matrix. Take the entries of the tensors coming from derivatives of w and k not to be independent and identically distributed, but to be correlated. The results survive again. You could also say, well, what if there are some leftovers, for example, of n equals 2 structure? You want to put in some special properties of the Riemann tensor. Also, the results survive. But there's a massive change you can make, which is physically motivated, which is just that if you decouple two sectors, in no sense are w and k random functions democratically of all of their arguments. They're decoupled. If that's the case, then the arguments that we made for all n fields don't immediately apply. So let's see how that works in an example. Suppose I give nh, where h stands for heavy. Nh fields large supersymmetric masses. Then if they have large supersymmetric masses and the Goldstino lives in the light sector, the only fields I have to think about for potential instabilities are the nl, which is n minus nh, light fields that are left over. And if the number of light fields is small enough, well, the probability would go like e to the minus nl squared, which is vastly larger than e to the minus n squared. So this suggests that a fruitful corner of the landscape to look is one where people have already been looking. Let's say in type 2b string theory, give the complex structure moduli masses that are as large as you can manage, and then study cases with small numbers of Keller moduli. Conveniently, this is the case where one can actually do the analysis, as we heard in Rommel's talk yesterday. Okay, so why do I say there is still a landscape? To be quite clear here, I do claim that in view of this, our results are representative of the effective theories descending from string theory to the extent that those effective theories involve random supergravities. But that doesn't cover the whole space of possible supergravities. There's a large non-democratic space where things are decoupled into a large number of heavy fields and a small number of light fields. And if the degeneracy comes from the large number of heavy fields, as in Buso-Polchinski, then the total number of vacua can still be larger than 10 to the 120. Okay, so now let me say a few words about applications in the last couple of minutes. What you'll hear about in David's talk tomorrow is that you could try and use these methods to study supersymmetric vacua. So as we all know, supersymmetric ADS vacua are permitted to contain tachyons allowed by the Breitenlotter-Friedman bound, and they're generally thought to contain such tachyons. But let's ask a precise question. What's the actual probability that a SUSY ADS vacuum does not contain any tachyons? So all the scalars have positive mass squared. The reason you might want to know about that is if you're thinking of a model of uplifting, then as Gary explained, uplifting tends to introduce additional instabilities. Certainly it's hard to imagine that uplifting will cure a large number of instabilities. So the probability of the existence of an uplifting is, roughly speaking, bounded above by the probability of no tachyons in ADS. Now, I won't be precise about that here, although one can do so. So let's just study this, the probability of no tachyons in ADS. And as you can hear from David tomorrow, the probability is e to the minus 2n squared times w squared over the supersymmetric mass scale squared in Planck units. So you see that it clearly depends on the ratio of the superpotential to the supersymmetric mass scale. One final application is that our matrix model for the Hessian has some successes even for very small n. So here's a case with n equals 3. If you put a D3 brane in the conifold, the corresponding theory has 3 complex fields, so our n, remember, is the number of complex fields. And here is the result of simulations of the eigenvalues of the Hessian matrix from 10 to the 7 realizations of the potential that we computed in this work. The potential for D3 branes on the conifold attached to a stabilized convectification. You don't see 6 eigenvalues there because eigenvalues 3 and 4 and 5 and 6 are degenerate to high accuracy. Okay. And if we use a simplified version of the matrix model that I was discussing here, so here are the 2 Wishart matrices, and here's the Wigner matrix, then one sees a broadly similar structure. Now, the match is not perfect, but it's remarkably good given that this was a large n expansion and n is 3. Okay, let me conclude. Using random matrix theory, we obtained an analytic expression for the scalar mass spectrum at a generic critical point in an n equals 1 supergravity theory with n scalar fields, with n large. I argued that the Hessian is accurately modeled as the sum of 2 Wishart matrices and a Wigner matrix. The probability that a generic critical point is a minimum is e to the minus constant times n squared. So an overwhelming majority of critical points are unstable saddle points, not metastable vacuum. An approximately supersymmetric critical point is considerably more stable, although not as stable as previously thought. The probability of stability is e to the minus constant n log n. And a supersymmetric ADS vacuum has some chance to have no tachyons, given by this probability. So I think there's a rather promising outlook for using these kinds of techniques to study a large number of questions involving stability in the string landscape and dynamics in the string landscape. Our matrix model for the Hessian could be used to study the probability of stability in a given model, the mass spectrum in a vacuum, or the mass spectrum at a critical point, and also the dynamics of the light fields as relevant, for example, in multi-field inflation. So I think that random matrix theory provides a powerful set of tools to study the vacuum structure of string theory. Thank you.
One of your assumptions was to have only a potential which comes from F terms. So do you think your structure will be changed if you include also D terms, because D terms also contain interesting gauge fluxes and can be used for stabilization and can be also used for uplift?
Right, yeah, so this is an interesting question that we are looking into now. One thing that you can say is that the D-term potential can in some cases give additional stability, but to have total stability, I mean, to really cure a large number of tachyons, you would want to have as many D-term contributions as there are moduli. So it's not clear that that's a generic configuration. If you just have D-terms for a few gauge groups, then it doesn't change the structure very much. It adds, if you imagine you have some large n number of fields and then some small number of D-term contributions, then It's mostly like a constant plus contributions to a small subsector of the eigenvalues. But we are looking into making more general statements about this.
Yeah, because there are also this paper in N equal 2 with D terms by von Pluyen, and they found the zeta and also stable, so it can make a difference.
Yeah, it definitely improves stability properties in some cases. Yeah, and this is clearly exclusively an n equals 1 result.
Very.
So in the scenario where you have the separation of scale to improve the stability, it's true that the complex structure model can be very happy, but that's where the 10⁵ comes from. So you also need a large number of critical points to bind your stable.
I think I agree completely if I understood. I mean, you're just saying that when I was arguing that if I give the heavy field large supersymmetric masses and I have a small number of light fields, you could still have a very large number of vacua there, even if NL is small, right? Even if suppose you have one critical point in the light one metastable de Sitter vacuum in the light sector, but for that de Sitter vacuum, you can choose a large number of different solutions in the heavy sector, then you could have a large degeneracy.
Okay, Joe.
So I guess often in string theory, the moduli that there are these sort of special decompactification directions where you know that the potential is zero along that direction. So there's a sort of special kind of boundary, which which often then is important in kind of arguments for minimum, because you can say, well, let's say it's 0 to infinity, it's positive, a small volume, and it's negative somewhere in between, so therefore minimum E.
That's right. If the number of such fields were order n, then I think it would play a critical role. If the number of such fields is small, I would be surprised if it could affect instabilities that are as common as these. And I don't mean common in the sense that a large fraction of critical points have at least some. I mean that at almost every critical point, the number of tachyons is a reasonable fraction of n. So indeed, in models with few parameters, those effects that you're describing are extremely important for providing stability. I would think that here it would affect a small number of the eigenvalues.
Back.
The sign of the cosmological constant didn't seem to matter. I mean, it's like you found that non-SUSY ADS, or non-SUSY DS, there's no difference in the likelihood for tachyons. But
well, there was one thing that
there's
one thing that I suppressed. Okay, so it's tricky which things you choose to hold fixed. I suppressed the so-called shift contribution to the spectrum. I just found the shape. That was for simplicity of presentation. But in fact, the shift is f squared minus 2w squared, not f squared minus 3w squared. So actually, as you increase the cosmological constant in this model, the stability properties improve. Now that's if you increase the cosmological constant holding everything else fixed. But you could instead try to keep the cosmological constant fixed and scale the supersymmetric masses or something like that. It's not at all clear to me how one should slice up that parameter space to ask these sorts of questions. What is the dependence on the cosmological constant? And in particular, Gary and company and we found different results for the dependence on the cosmological constant, which are entirely compatible because we're just holding different things fixed. So I don't know what the right question is to ask about that just yet.
When you talk about decoupling two sectors, did you mean that the Kähler potential is the sum of light and heavy? Or what did you
So
mean?
at least if the Kähler potential is a sum and the superpotential is a sum, yeah.
But this is not valid beyond, I mean, that's true. Classically, it's not necessarily true.
That's right. Sure. So what you could include, for example, is loop corrections or something like that spoil such decouplings. So when I say decoupling here, you can still give fields large supersymmetric masses and have the corresponding supersymmetric masses that get communicated to the light fields unwittingly by virtue of these sorts of cross couplings you're referring to be suppressed by a factor of the coupling strength. So it's still possible to decouple them partially.
I have one question. You're suggesting that these 10 to the 500 vacua, which we need to have an anthropic principle to get a very small cosmological constant, are coming from adjustments of VEVs of super heavy fields. So there's sort of a non-decoupling of the heavy physics from this very small energy associated with the cosmological constant. Do you have any idea how that seems to make sense?
I wouldn't say that it's a strict non-decoupling. I mean, these effects appear only as constant parameters in the low energy Lagrangian. So it's not like they play a direct dynamical role. I think it seems to me like a consistent picture in which you have a large number of choices at some high scale, you integrate out the heavy physics, and you're left with a memory of that number of choices in your low energy effective theory. And then the low energy dynamics only cares about the high scale physics through one parameter, the cosmological constant.
Right, but then the low energy dynamics has to find the right heavy vacuum, which gives you the small cosmological constant.
Oh, I make no claim that in such a picture you could describe a good selection principle by which you explore the different heavy vacuum until you find the one that has the right cosmological constant. No, absolutely not. This is just a counting result at this level.
Okay, let's thank the speaker again.